Hello, this is week 2, time value of money. Today, we're going to be looking at 3 primary topics: interest and interest rates, compound and simple interest, as well as effective and nominal interest rates. Keep in mind that for this chapter, there are additional topics which will be covered in the next set of videos. To begin, engineering decisions frequently involve trade-offs among costs and benefits occurring at different times. Why different times? Because cash flows don't necessarily occur and converge all at the same point. Some cash flows are given in the future, some are to be obtained now, and it is the job of engineering decision making to be able to make those cash flow assessments. And typically, we invest in a project today to gain future benefits. As well, the key to making comparison of benefits and costs that occur at different times is the use of an interest rate. So what exactly is an interest? Interest is the cost of borrowing money. Interest is the compensation for giving up the use of the money and the difference between the amount loaned and the amount repaid. And that is what the premise of this course in many of its upcoming chapters will be centered around the use of that interest. An amount of money today, P, can be related to the future amount, F, by the interest amount, I, or in smaller case, interest rate. As you can see this formula here, F equals to P times, in bracket 1 plus I, whereby F is going to be the future worth, P is the present worth of F, times 1 plus smaller case I, which is the interest rate. The dimension of an interest rate is typically dollars and time. For example, if $1 is loaned at 9% interest rate, then $0.09, or in this case 9 cents per year, will be paid in interest per time period. In this particular example here, we have not provided you with a time period. The period over which interest is calculated is the interest period. The longer the interest period, the higher the interest rate must be able to provide the same return. And that is done in many different business situations whereby the longer that loan is issued, the higher the risk, and therefore the vendor, the bank, or whomever that's issuing that loan will require a better upside in terms of the gain. Hence, interest rate has to be higher if it's a longer interest period. This table summarizes the most commonly used interest period, such as semi-annually, which is twice per period, or once every 6 months. Quarterly would be 4 times a year, which is once every 3 months. Monthly would be 12 times per year. Weekly would be 52 times per year. And daily would be 365 times per year. Continuous would be as many as possible and continuously during that period. And there are particular calculation methods for continuous. So let's now understand what is compound interest. In the world of interest, it's generally classified into 2 ways. Simple interest, if the amount P is lent for one period at an interest rate I, then the amount repaid at the end of the period is F equals to P times 1 plus I. Whereas compound interest, if it's more than one period, interest compounded. At the end of each period, interest is added to the principal that existed at the beginning of that period. Compounding means that you're adding the interest to the principal, and the next period, you're adding the interest based on that new total each time. Compound interest, if an amount P is borrowed for n periods at an interest rate I, the amount that must be repaid at the end of n period is F equals to P times bracket 1 plus I to exponent n. This n is very key. This method of computing interest is called compounding. Compounding assumes there are n sequential 1-period loans, and at the end of each period, the amount borrowed plus interest added in that period is borrowed for the next period. Compound interest would be the total interest on the loan over n period is I, smaller case c, or in this case subcase c, is referred to as the compound interest equals to F minus P equals to P times 1 plus I to exponent n minus P. interest period used with the compound interest method is called the compounding period. Let us take a look at an example. If you were to lend $100 for 3 years at 10% per year compound interest, how much interest would you get at the end of the 3 years? Well, if you lend $100 for 3 years at 10% compound interest per year, you'll earn $10 in interest in the first year, and that $10 will be lent along with the original $100 for the second year. Thus, in the second year, the interest earned will be $11. How do we get that? Well, it's $110 times 10%. Then the $11 is lent for the third year. This makes the loan for the third year being $121. And you see here $12.10 is 121 times 0.1, which is at 10%. And interest would be earned in the third year. And at the end of the 3 years, the amount you are owed will be $133.10. The interest received then is $33.10. You can see this calculation helps you summarizes all of the steps that we just talked about into one simple line that gets you to $33.10. This table breaks that down as well in terms of the 3-year period, the amount lent, the interest amount, and the amount owed at the end of that year. When we say simple interest, this is interest without compounding. Interest is not added to the principal at the end of the period. So in the most simplistic way, it's going to be interest equals to P times I times N, whereby compounding simple interest amounts equal if N equals to 1. And as N increases, difference between accumulated interest amounts for the two methods increases exponentially. The conventional approach for computing interest is the compound interest method. Simple interest now is rarely used today. So it is more common now that we utilize the compound interest method for calculations. On this table, you can see an example of a compound in simple interest at 24% per year for 20 years. You can see for simple interest, whereby the x-axis is year, the y-axis is accumulated interest. Simple interest does not increase very much, and it is essentially regular intervals of amount, whereas compound has an exponential effect due to the fact that the interest is added to the principals and therefore compounded to the next cycle along with the new interest added to the principal again and again and again. Hence, you see the steep increase in terms of the curve. Take a look at this screen. This is found in your ebook, whereby it has a visualization. What happens when you have a set of nominal interest rate that you can configure, the frequency of compounding, whether it be quarterly, daily, biweekly, and other variations, the initial investment, the number of years funds are invested, and you can view the calculation details along with the simple interest accumulated versus that of the compound interest accumulated, and as well as the graph. So you can see if the interest is adjusted, obviously, then the amount that goes up year after year will change. Similarly, if you're looking for which compound period will give you the maximum yield, or on the reverse side, the lowest amount of interest that you have to pay, then you will want to pick the compound that makes most sense. As well, initial investment will help decide how much compounding effect will take place in conjunction with the interest rates applied. The number of years of the funds is also affected as well. And so if you click on View Calculation Details in the ebook, you'll find that actually breaks it down in terms of the table based on the information that we've just entered. So moments ago, I entered 7 years, right? In terms of compound interest, this is what happened. The end of year value, what will be the simple interest, and what will be the value of the year end. And so you can do that comparison as well. If interested, you can certainly download some of these visualization into a spreadsheet, and you can further configure them for your own learning as well. Now let's get back to the slides. Next, we're going to be talking about nominal interest rates. Interest rates are stated for some period, usually a year, and computation is based on shorter compounding subperiods. And in this section, we consider the relationship between First, nominal interest rate stated for the full period, and then the effective interest rate that results from the compounding based on the subperiods. Unless otherwise noted, rates are generally nominal annual rates, calculated by multiplying the interest rate per compounding period by the number of compounding periods per year. Supposedly, R, lowercase, is a nominal rate stated for a period of 1 year, consisting of M, lowercase, equal compounding period subperiods. Then the interest rate for each subperiod is calculated as I equals to R divided by N. Now, an effective interest rate is the actual but not usually stated interest rate, which is found by converting a given interest rate with an arbitrary compounding period, normally less than a year, to an equivalent interest rate with 1 year compounding period, shown as below, where IS is interest rate over a compounding subperiod, IE is the effective interest rate over a longer period, and M is the number of subperiods in a longer period. Let's take a look at an example of how this works. What is the annual effective rate equivalent to a nominal rate of 12% compounded monthly? The nominal interest rate is given as R equals to 12%, and the number of corresponding periods per year is M equals 12, and this gives I equals to R divided by M, which is 0.12 because of the percentage, divided by 12, right? Because we're looking at monthly, therefore it would be 0.01. Then you apply that into the interest equation here, which is IE equals to 1 plus IS minus 1. And you can see, once you go through the numbers, you get approximately 12.7%. And an interest rate of 1% per month compounded monthly is equivalent to an effective rate of approximately 12.7% per year compounded yearly. You can see in this method, we are actually converting what would be seen as a relatively straightforward understanding of the fact that it's 1% per year or 12% compounded monthly. But if you want to convert that into an annualized or compounded annualized amount, then that gets into 12.7% because you have to factor in the compounding effect. Let's go to the next example. Burnaby Payday Loans lends money to clients between paychecks at a rate of 5% interest per week. What is the nominal interest rate for these loans? And what is the effective annual interest rate? Well, the nominal interest rate is 5% times 52 equals to 260%. Recall that nominal interest rates are usually expressed on a yearly basis, and the effective yearly interest rate can be found by substitution. Once you plug it in into this equation here, IE equals to 1 plus 0.05 exponent 52, because it's per week, minus 1 gets you to 11.64. The Burnaby Payday Loans charges an effective annual interest rate of about 1,164% on loans.